What's going on, everybody? Welcome back to my YouTube channel. Well, we have a beautiful question on the board that we are going to be solving. And the question says, find the value of x for which 1 to the x is equal to 2. Well, we can decide to take either the log or the ln of both sides because we have an exponent, which is a variable. So let's take the ln of both sides. So I'll take the ln of 1 to the x, which is on the left hand side, equal to the ln of 2. Now our next step will be for us to apply the law of logarithm, which also applies to ln, which says when I have, for example, ln of a to the n, this is equal to n ln of a. So let's apply this property to what we have here. So that means this expression now becomes x ln of 1. And this is equal to ln 2. Now, since we are looking for x, the coefficient is ln of 1. So we're going to be dividing both sides by the coefficient, which is ln of 1. So I'll divide the left-hand side by ln of 1. And I'll divide the right-hand side by ln of 2. Now you notice that ln1 will be gone, leaving behind x to be equal to, now, this is supposed to be ln1. Now notice that ln1 is equal to 0. That's just it. That means we're going to be having ln2 divided by 0. And since we're having 0 on the denominator, this is undefined. That means we do not have real solutions, but we're going to be having a complex solution. Now, how do we solve for complex solution? In order for us to, get the complex solution, that means we're going to be using the Euler's formula. For example, we know that e to the I theta is equal to cos theta plus I sine theta. We can decide to say, okay, when theta is equal to 0, I'm going to be putting 0 to wherever I see to theta. So this is e to the I theta is equal to cos. Remember, theta is 0. So this will be 0 plus I sine 0. Okay, since theta is 0, it is easy for me to just put 0 here. And this gives us cos 0. Cos 0 is actually 1 plus I times sine 0 is 0. So we've got 1 here. Now, what if we have to replace theta with 2k pi? That means, what if we said let theta be equal to 2k pi? So let's go back to what we have here. So this is e to the I times 2k pi. Remember, I'm replacing theta with 2k pi. But in this case, k should be a positive integer. And its value can range from, 1, 2, 3, and like that. Very good. So we're replacing theta with 2k pi. So we have e to the I times 2k pi equal to cos 2k pi, then plus I sine. In place of theta, we put 2k pi. Now, we're going to be testing from k equal to 1, 2, and 3. So let's try for when k is equal to 1. So let's say let k be 1. If k is 1, we have e to the I times 2 times 1, that's 2. We have e to the I times 2 pi equal to, this is cos 2k pi. K is 1, that is 2 times 1 times pi, that is 2 pi. So cos 2 pi plus I times sine, we have the same thing, 2 pi. Now, actually, cos 2 pi is actually 1, while sine 2 pi is 0. And when you multiply that with I, we're going to be having 0. So this is 1 plus 0, which gives 1. Now, let's try for when k is equal to 2. Let's do that on the next slide. Okay, now let's try for when k is equal to 2. So we can just say let k be 2. Now, if k is 2, we're going to have e to the I. K is 2, so 2 times 2, that's 4, times pi is 4 pi. So I times 4 pi. This will give cos. Remember, this will be 2 times 2 times pi, that is 4 pi, plus I times sine. This is going to be 4 pi. The same as what we have here. Now, cos 4 pi is actually 1, and sine 4 pi is 0. So 1 times 0 times I is 0. So that means we have 1 plus 0, which actually gives 1. So we can see that we have the same thing as we did when we set k to be 1. Now, what about we try for k be equal to 3? When we try for k equal to 3, let's go again. We have e to the I. Now, 2 times 3 times pi gives 6 pi. So I times 6 pi. So this is equal to cos. This is going to give us 6 pi because 2 times 3 times pi is 6 pi. 6 pi plus I sine 6 pi. The same thing. Now, notice that cos 6 pi is actually 1 and sine 6 pi is 0. And when you multiply 0 by I, we also have 0. So 1 plus 0 is 1. So we also have the same thing when k is 1, k is 2, and k is equal to 3. So it goes on to say that whenever we have an expression of e to the I times 2k pi, as long as k is an integer, this should be equal to 1. So we're going to go back to our question. Our question which says 1 to the x is equal to 2. Now we're going to be substituting e to the I times 2k pi for 1. That means wherever I see 1, I'm going to be substituting this. So let's do that. You notice we have 1 here. I'll be putting e to the I times 2k pi. And remember, this one is raised to the x. So I'm going to be raising this expression to the x equal to 2. Now, our next step will be for us to apply indices, which says when I have a to the m, and if this is raised to the n, this is equal to a times n is mn, which means powers multiply. So I'm going to be using this x here to multiply this exponent inside. And when I do that, I'll have e to the I times 2k pi multiplied by x. And this is equal to 2. Now, our next step will be for us to take the ln of both sides. So I'll take the ln of what I have here, ln of e raised to the I times 2k pi x equal to, I'll take the ln of 2. Now let's move on to the next slide to continue. All right. Now let's apply this famous law or property of logarithm, which says when I have ln of a to the n, this is equal to n ln of a to what we have here actually. Now we take the exponent, which is I times 2k pi x times ln of e. And this is equal to the right hand side, ln 2. Now obviously, ln e is actually 1. And if we have to multiply 1 by this expression, we get the same thing. So 1, this is I times 2k pi x equal to ln of 2. Now we're looking for x, but x has coefficients I times 2k pi. So in order to get x, I'm going to be dividing both sides by the coefficient, which is I times 2k pi. So I'll divide the left-hand side by I times 2k pi. I'll divide the right-hand side by I times 2k pi. Now notice I times 2k pi will cancel out, leaving behind x to be equal to ln 2 all over I times 2k pi. Well, there is something we need to know, that it is inappropriate that we have I as a denominator. So we need to get rid of I from the denominator. And in order to do that, I'll multiply the numerator by I. I'll also multiply the denominator by I. So we have ln 2 times I gives us I ln 2 all over. Now I times 2k pi times I. When these two I comes together, we have I squared, right? Cool. Times 2k pi. And actually, we know that I squared is negative 1. So this gives us I ln 2 divided by, this is negative 1. So let me put negative 1 there, times 2k pi. And when we multiply this with this, we get I ln 2 all over negative 2k pi. But actually, this is written appropriately after dividing as negative I ln 2 all over 2k pi. So this is our final answer. But let's make this point clear. If k is positive integer, and that means negative integer should also work here. So we're not only limiting k to be positive integer, except that k is not equal to 0. So that means when we try negative integer, we can also have solution for this. Now, this is it.